Welcome back to the session on graphs. So in this tutorial we are going to see graph traversals. So continuing with some of the more definitions, what is a subgraph? So a subgraph is a part of the given graph. That means it is going to contain some subset of vertices and some subset of edges. So consider a graph be like this: A, B, C, T, and E. Okay, so I can consider a subgraph as like this, which will contain maybe all vertices or maybe some subset of the vertices. Similarly, I can have some subset of the edges. So that is called as a subgraph. So what is a spanning subgraph of G? A spanning subgraph of G will contain all the vertices of G and may not contain all the vertices of, it will contain all the vertices of G and may not contain all the edges of G. So for example, if I take A, B, C, E and D like this, let's say this is my graph. So a spanning subgraph can be something like this. So in this case, if you see, it is containing all the vertices of G but will not contain all the vertices of, all the edges of G. Now what is a connected graph? A connected graph is called as connected if there is a path between each and every pair of vertices. So if you take an example, this graph itself, between each and every pair of vertices there is a path. So I can reach from A to E via A, B, E, or I can reach via A, D, C and E. So if a graph is having path between each and every pair of vertices, it is called as a connected graph. So what are connected components? Connected components are basically formed from the subgraphs. So if you observe here, this is a separate component and this is another separate component with only a single vertex, and this is another separate component with two vertices. So here within each and every component the vertices are connected. That means within this component, from any vertex to any vertex there will be a path, and each and every single isolated node is considered as an independent component, and here this is another component. So if you look at this example, there are totally 3 connected components, this being the one, this is the second one, and this is the third one. So these are 3 different connected components in the graph. So what's a tree? A tree contains all the vertices of the graph and will not contain all the, it may contain all the edges, it may not contain all the edges. But the fundamental difference between a graph and a tree is that a graph will contain cycles whereas a tree will not contain cycles. So what is a forest? So a forest in an undirected graph without cycles is nothing but something like connected components. You can say that connected components of a forest are trees. For example, if I take the single vertex and if I take vertices like this, and let's say I can take some vertices like this. Okay, so here each one of them is an independent tree. So when we have multiple independent trees like this, all of them put together will form the forest. So what are the importance of the graph traversals? So in undirected graph, so just before going into what is the importance of graph traversal, let's understand what is the definition of a graph traversal. So a graph traversal is nothing but a combination of or a sequence of visiting vertices and taking edges. So if you look at a graph is formed by basically a set of vertices and a collection of edges. So in a sequence, if we start visiting from one vertex to another vertex by taking their respective paths, that is called as a graph traversals. So so one of the fundamental example that I can give is like a Google map, where every junction or the intersections are actually like vertices, and the roads that are connecting these intersections can be taken as edges. So if I want to travel from point A to point B, I may be traveling across multiple intersections, I mean junctions, by considering multiple roads. So that will form my graph traversal from point A to point B. So in an undirected graph, what are the different advantages of doing a graph traversal are given here. So first one is computing paths. So doing a graph traversal, I can understand what are all the different paths that are available between different vertices, and computing minimum cost paths. So earlier in the videos I have already mentioned that an edge can take a weight. For suppose like I have to travel from point A to point B, so the cost incurred for me to travel from point A to point B can be taken as a weight. And the weight need not be always the cost, it can also be something like time, or it can be the distance between point A to point B, or it can be anything like reward or a penalty. So computing minimum cost paths is also possible when we do a graph traversal. Then testing whether a graph is connected. So just now we have seen that a connected graph is nothing but take any pair of vertices, there should be a path between those two vertices. So we can also check whether a graph is actually connected or not. And also computing connected components, that is also possible using graph traversals. Then identifying cycles, because whenever we traverse a graph, and if we are while traversing, if we reach to a vertex which has already been visited, then I can consider that we have detected a cycle. So in directed graphs, what are all the different things that we can do using graph traversals are given here. So computing directed paths and checking reachability. Reachability is nothing but from given any two vertices, checking whether there is a path between these two vertices is called as reachability, whether I can reach from A to B or not. That's what is mean by reachability. And determining whether G is acyclic or not. So in a directed graph which doesn't have cycles is called as a directed acyclic graph. So checking whether given a graph, checking whether there is no directed cycle is called as a directed acyclic graph. So that's the third one. So when we are looking into graph traversals, what are all the different edges that are possible? So we are going to look into some of the examples. So I have taken a simple example here where multiple cities are given and the roads that are connecting these cities are given. So when we are traversing, the blue lines are here actually, the forward edges. That means these are the ones that are taken. So in this example, let's say I have started from this BOS, so I come to JFK, and from then I am traveling to DFW, and then LAX, and then ORD, and from ORD if I am taking a path again back to DFW, this will be treated as a back edge. This will be considered as a back edge. The reason is DFW is already visited, and from ORD I am trying to visit a city that is been already visited, so that will be treated as a back edge. So typically in graph traversals we have three fundamental types of edges: forward edges, back edges, and cross edges. So I'll just tell the difference between the three. Forward edges are those edges which we are trying to explore. For example, from BOS there is a possibility that I can go to SFO or I can come to JFK. So these are the two discovery edges that are available for me. So here in this example we have taken a path from BOS to JFK. So I'll mark this path as a forward edge. So the path that is taken to reach a vertex is treated as a forward edge, and a backward edge represents an edge that is connecting to a vertex which has already been visited. So for example, in this case the edge from ORD to DFW, this dotted blue line is considered as a back edge because this is connecting to a city which is already visited, which is nothing but DFW. So a cross edge is nothing but the edge that is there between the siblings. So in order to explain this, let's reframe the definitions of forward edge, back edge and cross edge. So when we are representing this in the form of a tree, a graph traversal can be represented in the form of a tree. So for suppose BOS, I started from BOS, from there I visited JFK, and from there I have traveled to DFW, and from there I have traveled to LAX, and from there I have traveled to ORD, and from ORD there is an edge that can go back to DFW. So from JRD there is an edge that can go back to DFW. So if you observe this, when we represent the graph traversal in the form of a tree, the edge that is going from ORD to DFW is nothing but an edge that is going to one of its ancestors. So an edge that goes to one of its ancestors is called as a backward edge. And similarly, we can frame the definition of forward edge as an edge that is going to its descendants. So if you see here, from BOS to JFK and JFK to DFW, these are all the edges that are going towards the descendants, so they are called as forward edges, and the edges that are going towards the ancestors are called as the backward edges. Now cross edges are those edges which are neither going to the ancestor nor going to the descendant. So cross edges can be something like the edges between the siblings, etc. So those are treated as cross edges. So you can see here in the example that is given here, all the black dotted lines are actually treated as the cross edges, because they are the edges which are neither forward nor backward. That means they might be connecting some of the siblings in the tree, then they will be treated as a cross edge. So coming to the first traversal algorithm, which is DFS. So let's start from A. So a DFS traversal will always explore the edges in the depth first order. So I start from A. So I have three possibilities. I can go to B, I can go to F, and I can go to E. So let's say we are taking the path B. So I mark this edge as a forward edge. Then from B I have the possibility that I can go to C or F. Let's say I am taking the path C. So I mark this as the forward edge. So likewise, we travel from C to D and D to G, and when I come to G, I have 4 different possibilities, either from D to C, D to J, D to K, D to L. So if I take D to C, that's going to be a edge which is going to go back to a vertex which is already visited. So we are going to mark this as a back edge, which is represented in the dotted arrow. So when we are doing a DFS traversal, we are understanding that we have a discovery edge, and when we discover that edge and go to a particular vertex, we mark this vertex as forward edge, and whenever we come across an edge which is pointing back to an ancestor, we mark that as a back edge, and whenever we visit a particular node, we mark it as a visited vertex, so that we know that if an edge is going back to the visited vertex, we can mark it as a back edge. So after G we have explored J, and from J to I, and I to E, and E to F. So the DFS traversal has proceeded till F. When we reach F, the other possibilities that I have are A and B, but A and B are already visited, so I mark them as backward edges. So I reach a point F which is a dead end. So what DFS traversal will do? DFS traversal will trace back and check for the other possibilities. That means it will backtrack the edges. So we will come back to E. I will see if from E whether I can reach any of the vertices. If I cannot reach any of the vertices, mark all the other edges which are forming cycles as back edges. And then I trace back to I, then we trace back to, once we trace back to I have other possibilities that I can reach M. So we start visiting M, and then I will visit to N, and then K to N to K, and K to O. Once I reach O, I visited a vertex which is a dead end. That means I don't have any other possibilities, I don't have any other discovery edges. So we again backtrack to K. From K, do I have any other possibilities? No. So we just mark everything as back edges. and then we trace back to n, and similarly we come back to m to I, and I to j, j to g, and from g, do I have a possibility that I can visit some of the vertices which are unvisited? Yes. So what do? We take the path from g to l. So we take the path from g to l, and from l I have two different possibilities, either to h and p. So I take h. Once I reach h, it is a dead end, so we again trace back to l and we visit the p. So this is how a DFS traversal will work. So just giving you a summary of the DFS traversal. So we start from a vertex A and we proceed with marking a particular edge as a forward edge if we have taken that particular edge, and all the edges that are leading to the ancestors, that means all the edges that are leading to the vertex that is already visited, all those edges will be marked as back edges, which are represented in the dotted lines. And whenever we reach a dead end, that means we cannot explore any other further edges, we backtrack to a vertex from where we can explore the other edges. So what are the different properties? DFS traversal starting from vertex S visits all vertices in the connected component of S, and the discovery edges form a spanning tree of the connected component of S. So if you carefully observe this, when you do a DFS traversal, as we are marking every edge that is going back to the vertex which is already visited as a back edge, that indicates that in this particular graph, if we remove all the back edges, that will give me a spanning tree of the graph G, because a spanning tree is a tree which doesn't have any cycles. So if we remove all the back edges, this indicates that we don't have any cycles in this particular graph. And also, let's say I have another node somewhere around here, let's say it is Z, marked as Z. So when I run a DFS traversal, the DFS traversal will find out the all the edges and all the vertices in this particular graph. But a DFS traversal will terminate only when all the vertices are being visited. So what does that mean? That means initially DFS will run on this particular graph starting from A. So it explores all the edges that are there in this particular graph, and it terminates at after visiting at P. But when it terminates at P, the DFS algorithm will know that it has not visited all the vertices that are there in the graph, because Z is the one that is yet to be visited. So what DFS will do? DFS will run again on Z. So by knowing how many times the DFS algorithm is actually running, we can understand how many number of connected components are there in the graph. And DFS algorithm basically makes use of a stack for the implementation, and so as and when there is a vertex that is not yet visited in the graph, the DFS algorithm will rerun on that particular vertex, which will indicate that there is a connected component in the graph. So, and DFS algorithm is also used for testing the connectivity of the graph, because we can check, just like I said, we can check whether every pair of vertices are actually connected or not, and we can identify the connected components, because when there are connected components, the DFS algorithm is a recursive algorithm, so it's going to run again on the independent component that is isolated from the actual graph, which indicates that there are connected components in the graph. And also it is useful for computing cycles, because when we do a DFS traversal and if there are back edges, all the back edges will lead to cycles. So finally, coming to what is the complexity of a DFS traversal, it is given by order of n plus m, where, or I can treat it as where n is nothing but the number of vertices that are there, and m is nothing but the number of edges that are there. So why it is n plus m? So let's take a simple graph like this. So when we do a DFS traversal on this, we have to visit all the vertices and mostly all the edges except this edge, because if I take this edge, this is going to form a cycle, so we'll mark this as a back edge. So in that case, in the worst case, what will happen when we run a DFS traversal is that it will visit all the vertices and it will visit and it will visit m-1 edges. So that's the reason in big O notation we can say that the complexity is order of n plus m, where n is the number of vertices and m is the number of edges. So the concept of BFS we will look into in the next video.